If you ask a developer how to build an autonomous AI agent, you will likely get a simple formula. Write a clever system prompt and wrap a language model API call in a basic while loop. Put that pattern into production and it fails. Unbounded loops run endlessly, burning through API budgets as the model generates endless tokens, blows past the context window limit, or stalls completely trying to execute a broken tool. The Hermes Agent, built by Noose Research, operates on the opposite architectural thesis. In this system, the language model is treated as a simple, unreliable token stream. The actual agent is the defensive software harness surrounding it. To see how this works in practice, we're going to trace a single command, refactor the auth module, through the 6 stages of the Hermes harness. Following this real data path is the best way to understand how specific engineering decisions transform unpredictable text generation into reliable software. Harness engineering, not prompt engineering, dictates what an agent can safely accomplish in the real world. Our trace begins when a user submits the refactor the auth module command via a Telegram message. This initiates the project's defining structural bet. Instead of writing separate logic for a command line, chatbot, and desktop app, Hermes writes the core agent once. These adapters construct the exact same AI agent object and call a single method, run conversation. Every interface reads and writes to a shared SQLite store called SessionDB. This database acts as the absolute source of truth, holding all session metadata, search history, and model configuration. Because of this single core, unified state design, the agent applies the exact same logic and permissions, whether you invoke it from a terminal window or a mobile chat app. The Telegram command now enters the core engine, the React loop, where the model observes the request, acts on it, and observes the results. This loop is strictly guarded by a dual-bound defense mechanism. The harness tracks a hard maximum iteration cap and a shared iteration budget simultaneously. Each standard pass through the loop costs 1 budget unit. However, if the model writes a Python script that calls multiple tools internally via RPC, it acts highly efficiently. The harness recognizes this and refunds the budget unit for that iteration. The loop terminates for one of 5 reasons. Beyond a clean text response or a user interrupt, it relies heavily on a guardrail halt, a controller that actively detects when the model attempts to call the exact same failing tool with the exact same arguments and forcibly breaks the cycle. If the budget does run out, the system degrades gracefully. Instead of crashing, the harness grants the model one final, toolless API call to summarize the progress it did make back to the user. Inside the loop, the model attempts to act on our refactor command by accessing system tools. It has a massive surface area to choose from, 49 core tools and 174 distinct skills. Providing this capability comes with a steep technical cost. Every single tool schema must be sent to the language model on every API call, taking up valuable token space. Hermes solves this using the narrow waist pattern. All tools self-register, but they must pass through a single, central function called getToolDefinitions. This exact choke point aggressively filters out unavailable backends and sanitizes the data before wrapping it in an OpenAI-compatible format. Once a tool executes, the harness applies 3 tiers of defensive truncation to the output: a per-tool cap, a disk persistence limit, and an aggregate turn budget. By forcing all inputs through one uniform schema pipeline and rigidly truncating outputs, the agent maintains its massive breadth of capability without letting a single verbose tool blow out the context window. The model decides the best way to refactor the auth module is a destructive action. It queues a patch command to rewrite the live files. Before execution, this passes through the structured approval gate. This is hard-coded routing logic, not an unreliable prompt instruction telling the model to be careful. In smart approval mode, the request routes to a guard LLM classifier. The harness strips away shell comments, eliminating prompt injection vectors. The guard LLM denies the risky patch. Here, Hermes deploys its critical philosophy: deny and continue. Hard halts are architectural failures. They instantly dead-end the autonomous process and force the user to constantly intervene, which quickly leads to approval fatigue and rubber stamping. By routing the blocked response backward as standard tool data, the language model is forced to adapt. It can read the reason for the denial and intelligently ask the user for clarification or attempt a safer alternative command. Let's assume the model pivots to a safer plan, but it needs to recall the user's specific coding preferences to rewrite the auth module properly. Despite its advanced routing and toolgates, the memory structure inside Hermes is incredibly primitive. The built-in memory is just two flat, character-bounded markdown files, memory.md and user.md. Standard industry practice dictates complex, tiered memory systems with distinct core, archival, and recall layers. Hermes abandons all of that. The entire architecture revolves around one economic invariant. Prompt caching is sacred. Memory files are permanently locked inside the system prompt. Rebuilding this prompt on every turn breaks the cache, incurring a 10 times compute cost penalty. To prevent this, the gateway explicitly caches one agent instance per session, guaranteeing that the exact same bytes are restored every iteration. Memory remains small and flat because it must ride safely inside this locked, immutable prefix to keep the software economically viable. As the auth module refactor continues, the transcript of tool calls, errors, and responses grows large. The system is now caught in an architectural tension. It has a finite context limit that is rapidly filling up, but it absolutely cannot break the sacred prefix cache at the top. Context compaction is the single sanctioned mutation of past context. When the transcript hits 50% capacity, the compressor protects the head and tail, strips verbose tool results, and uses an LLM to summarize only the middle. By executing this precise middle collapse, the harness avoids hitting the context ceiling and keeps the model focused, all while leaving the sacred prompt cache untouched. The refactor completes. The final text response is sent to the user, and the entire interaction is persisted safely back into the session DB. Tracing this single command reveals the exact shape of a production agent. It relies on a unified entry point, a bounded iteration budget, a narrow tool waste, and a deny and continue gate, all operating underneath a sacred prompt cache. The language model provides the reasoning engine, but the defensive harness is what turns it into reliable software. Yet the Hermes security documentation provides a necessary reality check on this entire structure. No matter how elaborate the guard LLMs, filters, or approval gates appear to be, they are ultimately just heuristics applied to attacker-influenced input. The operating system remains the only true security boundary, but rigorous harness engineering is the only proven method to deploy autonomous logic safely into that environment.